All right, so we're now on section 9.3, starting on page 382. So the theories that we've talked about so far, Lewis theory we covered in chapter 8, and then we covered Vesper theory in this beginning of chapter 9, which is just the same as Lewis theory, but three-dimensional, honestly. So it still has some fallbacks, and one of those is that it cannot explain certain kinds of bonding, and it doesn't explain why things would bond. So the next thing we're going to talk about is valence bond theory. So we're going to take a little bit of a trip back to chapter 6 and look at those orbitals that we talked about in chapter 6, the S's, the P's, and the D's. We're not going to worry about the F's so much because they're never involved in bonding. We're just going to look at the S's, P's, and D's and how they bond and how they overlap to form bonds. So first of all, instead of showing them as lines, we're going to show them as an overlapped orbital. So here's our simplest, smallest molecule, which is hydrogen. Laser pointer here. Hydrogen, H2. Each hydrogen has, if I were to just write out its orbital, 1s with 1 electron. So that's the atomic orbital for hydrogen, is 1s with 1 electron. So in Lewis theory, we did connect the dots. Now we're going to look at the orbitals and how they are actually shaped to describe what's going on here. So an s orbital is spherically shaped. As far as in the images here, s's are always shown as kind of this yellow color. And when it is opaque, meaning you can't see through it, it means that that orbital is full. When it is transparent, such as the first two up here, these transparent ones, that means that it is half full, meaning there's 1 electron in it. And as we're going to see in a little bit, when you have one that is completely whited out, that means there's nothing in it. It's just an empty orbital. So again, empty orbital is just whited out. If it is transparent, that means there's 1 electron. If it's opaque, that means there's 2 electrons in it. So I have these two hydrogens, each with their 1s orbital and 1 electron in it, and they just come together and overlap their orbitals, and that is where the bond forms. So that's the general idea of valence bond theory, is you're going to overlap orbitals. So this is the simplest idea. Two s's overlap, pretty simple. We can also have different kinds of shapes overlap. For example, here I could have two p's overlap. So here's the two s's overlapping. Two p's, if they overlap, these lobes would overlap, and you'd get like this. Now notice that once they overlap, they go from being transparent, meaning there's 1 electron, to opaque, meaning there's 2 electrons, because now the 2 electrons involved in the bond have access to not just the overlapped area, but actually to the whole p orbitals on both atoms. So that's why it became opaque. They now have access to that entire area. Or you could have an s and a p overlap here. So this would be something like HF. The hydrogen's s orbital overlaps with the fluorine's p orbital. So those are the three main kinds of overlapped orbitals that we will see. We'll see in a little bit. You can also do it with D. So when this happens, it can happen on the axis here. So here's 2 fluorines. So I'm making F2 here. So if I look at fluorine, here is fluorine's 7 valence electrons. It's got 2 in its s, which I'm not showing here just because it'll get in the way. And I've got 5 in its p. So p has 3 orbitals. We've seen them before in chapter 6. It's got the p along the y-axis, along the z-axis, and along the x-axis. We're going to say that the one along the x-axis is the one that's only got 1 electron, so that's the one that is shown here as being transparent. It's only got 1 electron in it. Here's another fluorine, completely identical, oriented the same way. They come together along the axis, and these are going to overlap, and you're going to end up over here with the bond being formed here. So in this case, I'm not going to draw these, don't worry. You don't have to draw them, but you do have to describe what part of the valence orbital, which valence orbital is involved in bonding. So if I just said, describe the bonding of F2 using valence bond theory, you would say this singly occupied p orbital in fluorine overlaps with the singly occupied p orbital in the other fluorine. And that's all there is to basic bond theory. They're just going to overlap. Or if I said for HF, the singly occupied H1s orbital is going to overlap with the half-filled or singly occupied 2p orbital in the fluorine, and that's what is going to form the bond in HF. So that's the general idea of valence bond theory. Why do things bond? This is a question that was never really answered with Lewis theory, even attempted to be answered. Well, why would these things bond? So here I've got an energy diagram that has the internuclear distance, or as they get closer together, what happens to the potential energy? Now, energy systems prefer what? To be at high energy or low energy? Low energy. They prefer to be at low energy. If they're at low energy, they're happy. So as they get closer and closer together here, the distance between, the potential energy is going to start dropping and dropping and dropping until it hits this perfect spot where the energy is very low. As they get further and further apart, the energy is going to increase until they even out. When those atoms are so far apart, they're basically not interacting with one another. They get too close together over here, then the energy starts going up again because the nuclei, which are positively charged, get too close to each other and start hating each other and repelling. So that's the sweet spot. And this is for the H2 molecule. That's about 74 picometers, so we call that the bond length. So this is the first time we try to explain, well, why would they try to bond? They try and bond to lower their potential energy. Here's another molecule that has one center and two things coming off of it. So this is sulfur with two hydrogens. Now, if I look at these P's, so in sulfur, I've got two spots available for bonding. They're both p orbitals. What is the angle between p orbitals? I've got the y-axis and the x-axis. What's the angle between x and y? 90 degrees. So if I have a hydrogen come in and bond with that, and a hydrogen bonding with that, these two hydrogens should be about 90 degrees from each other. And sure enough, if you measure the bond angle in H2S, you get about 90 degrees. So this is another thing that valence bond starts to explain that you didn't get any of in Lewis theory, is why are those bond angles what they are? So we've got some bond angles here. Now this isn't going to explain all the bond angles, but it's going to start to explain it here. So in summary, overall idea, the bond forms when singly occupied, meaning there's one electron in it, atomic orbitals on the atoms overlap, two electrons shared in the region must be of opposite spin, so that's going back to the rules we learned in Chapter 6. Formation of the bond results in a lower potential energy, so that's why the bond formed. So a typical question from this section would be something like this. Hydrogen selenide, H2SE, is a foul-smelling gas that can cause eye and respiratory tract inflammation. The bond is approximately 92-degree angles. Use valence bond theory to describe the bonding in this molecule. So what do I mean by that is what bonded with what? So I've got selenium in the middle, and I've got the hydrogens. We're just going to draw just general hydrogen here. And then selenium is also, it's in the same family as oxygen, so this is going to look very similar to a water molecule. So we're going to have two lone pairs in the selenium. So this would be the Lewis theory of it. Vesper theory would tell us that this is going to be tetrahedral and bent. So we're going to look at this and say, okay, well, what actually is happening at the atomic level? What's happening with the orbitals? In these hydrogens, each of the hydrogen has what kind of orbital? What's the only orbital hydrogen's got that's got an electron in it? S, 1s. So the 1s has one electron. Now, in this setup, we've gone ahead and shown you the orbitals for selenium. This would not have been done before you normally in a homework question, but selenium has in its P, its S is fully filled. D, we're not going to worry about because it's not going to be involved in the bonding. So this is what we're really worried about, is that 4p orbitals. We've got 3 of them. All p's always have 3 orbitals. 1 of them's filled, and then 2 of them are singly filled. So these hydrogens are going to come in and bond where on the selenium? Good, the singly filled. So I've got a hydrogen with a 1s that's going to bond here, and I've got a hydrogen with a 1s that's going to bond here. And because we know p orbitals are 90 degrees from each other, we would expect a bond angle around 90 degrees. And so that explains the 90 degrees. So that's all I'm asking you for, basically. You don't even have to draw it. Yep. You would just say that the singly occupied 4p orbitals in the selenium will bond to the 1s orbitals on the hydrogen. That's all you have to tell me for this section. How do you feel about valence bond theory? Not so bad? Ready to hear about why it doesn't always work? Be excited. So here's why it's so great. Now why it's so not great. All right, has everybody got that one down? X out of this and look and see if we can explain the bonding in a different molecule. Sure, keep that. New slide. Let's try and use valence bond theory to explain the bonding in carbon dioxide, CO2. So it helps just because it's easy and quick and makes it visual to go ahead and draw the Lewis dot structure of these things. So carbon dioxide, carbon, oxygen, oxygen, do. And this is linear, so what is the bond angle? Good, 180 degrees. And sure enough, if we measure carbon dioxide out there in nature, it is 180 degrees. It's a linear molecule. So now let's try and explain the bonding here. Our central atom is carbon. Carbon has how many valence electrons? 4. So what orbitals are those 4 in? No, not 1s. What? It's got some in p, but also it's only got 2 in its p. What are the other 2? 2s. Good. So it's got 2s. How many electrons are in its 2s? 2. And it's 2p. We've got 1, 2, 3 orbitals. How many does it have there? 2. So according to valence bond theory, where is it available to bond here? The 2p. So it looks like can make 2 bonds. In carbon dioxide, how many bonds do I have to carbon? 4. What? How do I have 4 bonds? Okay, well, okay, so that's not going to work. But let's try something different. Let's say I'm going to take one of these electrons. Let's say I'm going to take that one, and I'm going to promote it up here. I'm going to call this C star. Star means it's now higher energy. That's okay. I'm just going to promote it. Erase that, get it out of our way. Now how many bonds can carbon make? 4. Okay, that's great. So we're going to come in and we've got 4 bonds. Here's the problem that we still have. If we draw this out, I've got an S around carbon. That's a sphere. Here's our little here. I've got our S is the sphere. Let me change colors here. Kind of do a purplish color. Yeah, that was blue. And then the P's are the dumbbells along each axis. Woo. Don't worry, I'm not going to make you draw it since even I can't really draw it very well. What is the bond angle between all of these P's? What are those bond angles all? 90 degrees. So how on earth can I come along with an oxygen over here and it make 180-degree bonds. It doesn't make any sense. So that's the problem with valence bond theory, is it cannot explain, how, first of all, how anything could possibly have more than 3 bonds, and it can't explain bond angles once you go bigger than 2 bonds. It just can't explain it anymore. Let's go back to this and say, well, how are we going to fix this problem and still be able to explain it? We're going to fix it by doing something called hybridizing. So what does the word hybridizing mean? If I'm going to hybridize something, that means I'm going to do what with it? What kinds of things get hybridized? Has anybody ever heard the word hybridize before? You've never heard the word a hybrid. What does a hybrid mean? It's a hybrid class. It's a mixture of 2 things. So a hybrid class, half online, half seated, right? What about, let's say, a mule? What is a mule? Good, a hybrid between a donkey and a horse, half donkey, right? Those are hybrids. You mix more than one thing together and end up with something that is somewhere in between. If you look at a mule compared to a horse and a donkey, it looks like something in between a horse and a donkey, right? That's the same idea here. We're going to do these orbitals. We're going to hybridize them, and we're going to end up with something that looks in between the 2. So we're going to do this for SPs, and eventually we're going to do this for SPs and Ds. So here's what it's going to look like. Let's try this with beryllium. Beryllium has 2 valence electrons. Normally they're going to be in 2s, but we want to be able to bond to that and have 2 things bond to beryllium. Let's say we want to do the molecule, which one am I going to do here? BeCl2. Drawn ahead here. Let's say I wanted to draw the molecule beryllium dichloride, which beryllium dichloride is linear with a 180-degree bond angle. Beryllium dichloride. So beryllium needs to bond to 2 things. Normal beryllium only has 2 valence electrons. They're both in the s. So just as I just did with the carbon, I'm going to make that a star, meaning I'm going to excite it. When I excite that, that is going to move one of those electrons up into a higher energy shell. But I still can't bond directly to it the way it is because I wouldn't get a 180-degree bond angle. I also wouldn't get equal bonds. One of these bonds is going to be bonded to an S, one to a P. But if I look at beryllium dichloride, I would expect these 2 bonds to be exactly the same. Same length, same angle, same strength. I expect them to be the same. So somehow we need to make these 2 things the same. So we're going to put them into our hybridization box, stick them in, hybridize them, and we're going to call these new hybrid orbitals, we're going to show here in green, sp orbitals, because it's made from an s orbital mixed with a p orbital. Rules: the number of orbitals that goes into the mixing box is equal to the number of orbitals that comes out of the mixing box. All orbitals that go into the mixing box have to come out the other side as a hybrid orbital, and all hybrid orbitals are going to be identical for that element. So now these 2, so looking at our S is a big sphere, our P is the dumbbell shape. Here's what our sp orbitals are going to look like. They're going to still kind of look like a dumbbell shape, but one side's going to be much bigger, almost trying to be a sphere. So that's our hybrid. It looks a half in between. Again, you're not going to have to draw these things, don't worry, but you are going to have to tell me what kind of hybrid orbital there is. Now these sp orbitals, now I've got 2 orbitals, they're going to align themselves the same as electron domains would. So I have 2 orbitals. How far apart are 2 electron domains going to try and get away from each other? What angle? If I had 2 electron domains, how far apart would they try to get? 180. Good. So if I look at this here, this is before hybridizing, this is after hybridizing. This is one of the sp orbitals, and here's the other one 180 degrees away from it. Now if I come in with my 2 chlorines, and I bond into those hybrid orbitals, I end up with identical bonds on both sides that are 180 degrees away from each other. Identical bonds on both sides that are 180 degrees away from each other. Let's go another one bigger. Let's go on boron. Boron, we know, likes to make 3 bonds, but if I look at boron normally, it looks like it can only make 1 bond according to valence bond theory. So first step of hybridization theory is promote electrons. electrons. I'm going to promote. So that's what this is. Write that word. Promote electrons. Hello. Promote. Promote electrons. So that's what this happened. I took this electron and I promoted it here. And that's what I ended up with here. I promoted electron. That's step 1. So you need to promote electrons so that you can have enough spots for bonding. So you promote as many electrons as it takes to make your bonds. Your second step is going to be hybridizing. You're going to hybridize however many orbitals you have for the number of electron domains. So in this case, say I'm making, what am I going to make here? Boron trifluoride. Let's do boron trifluoride. So boron trifluoride. And each of these fluorines has 3 lone pairs. So boron trifluoride, we know from VSEPR theory, is trigonal planar with a 120-degree bond angle, 120 degrees. So we made 3 hybrid orbitals, and these are called sp2 because they're made from an s and 2 p orbitals. I made it from an s and 2 p orbitals, sp2. Now I have 3 orbitals. They're going to line up just like 3 electron domains. So 3 electron domains lines up as a trigonal planar shape. So this is what it would end up looking like. So there's one of my sp2s, here's another of my sp2s, and here's my third sp2. And they line up in that pretty trigonal planar shape. Now I can come in with my fluorines and bond, and I end up with a nice trigonal planar shape. So let's take a quick aside. Yeah, keep that. And review how we're going to do this without drawing them. Because I know the pictures seem overwhelming. Don't worry, I'm not going to expect you to recognize the pictures or draw the pictures. I want you to be able to tell me what kind of hybrid orbitals you have and how many. So steps to hybridizing. Let's summarize this. Yes, red, black, small. Steps to hybridizing. Step number 1, promote. That means move to higher energy. Electrons to get as many half-filled orbitals as bonds. That's step number 1. Promote as many electrons as you need until you have as many orbitals with just 1 electron in them as you have bonds. So you now have enough bonding places. Again, electrons can, or you can only make bonds where you have 1 electron sitting there. It's Velcro. You've got to have a hook and a loop. One end has to have the hook, one end has to have the loop. If you don't have any electrons there, nothing will stick. Step 2 is you're going to hybridize as many orbitals as you have electron domains. Now, in the examples we just saw, this ended up being the same number, but I'm going to show you an example where this ends up not being the same number, and that's okay. Okay, can we follow these 2 steps? Sure. Let's make ammonia. Let's make ammonia. So, according to VSEPR theory, how many electron domains are in ammonia? 4. So what's the electron domain geometry? there's 4 things, that is tetrahedral. Good. So what's the ideal bond angle for tetrahedral? 109.5. Good. 109.5. It's going to be a little bit less here because that lone pair is taking up a little more room, so we actually end up with closer to 107. Now, if I were to look at nitrogen, say I wanted to describe the bonding here using hybrid valence bond theory. Nitrogen has how many valence electrons? 5. So the first 2 are going to be in that 2s. I'm going to have 2 there. And then 2p is going to have 3. 1, 2, 3. So first step of hybridizing is to promote electrons to get as many half-filled orbitals as bonds. Do I need to promote anything here? Why? How many bonds do I have? I have 4 electron domains, but how many bonds? 3. I've only got 3 bonds. Do I have 3 places for them to bond? Yes. So why bother with hybridizing theory? It's because of the bond angles. Let's look at this. P's. Again, what's the bond angle between P's? These are 90 degrees around, but we're expecting something that's slightly less than 109.5. So what on earth is going on here? So even though I don't need to promote to have enough bonding locations, I still need to hybridize to explain the bond angles. So I'm still going to do that second step. So step 2 is hybridize as many orbitals as you have electron domains. So how many electron domains do I have here? 4 electron domains. Whoop, forgot to make that small. So I'm going to hybridize 4 of these, which is all I have. So I put them into the mixing pot. How many orbitals will I get out? How many orbitals went in? 4. How many should I get out? 4. But they should all now look identical. 4 orbitals. Now, what will I call these orbitals? What went into it? I put an S in there. But how many p orbitals went in there? 3. So I'm going to call these sp3 orbitals. sp3 orbitals. Why did that one S suddenly get thick? I don't know. Now I'm going to put my electrons in there. So I'm going to have still 2 electrons in one of these orbitals. 1, 2, 3. So as far as the bonding goes, I have 3 hydrogens. So each of those hydrogens can go in where there is a singly occupied orbital there. So what about this guy over here? What's he doing? What is that? That's my lone pair right there. Good. That's the lone pair. Lone pair. Now, because I have 4 hybrid orbitals line up the same as electron domains. 4 electron domains has a bond angle of around 109.5. So now that explains my bond angles. So we're going to make a quick and easy cheat table to figure out how many electron domains we have equals what kind of hybrid orbital. Now let's first talk about D's, and then we'll make a table so we can cover them all in one table. Going back to here. So here's an example of making an sp3, but this is with carbon in the center, and we're making 4 bonds. I think we're making methane here. Yeah, we're making methane. So back in chapter 8, we had exceptions to the octet rule, and I said, as long as your third period or below, your central atom can expand its octet because it has that unfilled, just empty d orbital lying around. So what does that look like? Well, let's look at phosphorus. Let's say I have phosphorus and I need to bond into phosphorus with 5 different things. If I bond in with phosphorus with 5 different things, I need to promote an electron. Let me get my pointer. I need to promote this electron. Well, I can't promote it into the p's because that still wouldn't give me enough half-filled orbitals as I have bonds. I have 5 bonds. So I'm going to promote it all the way up to D. So when I promote it all the way up to D, again, that 3D is sitting there, it's just empty. I promote it all the way up to D. I'm going to hybridize all 5 of these. I get 5 orbitals out, sp3, and then a D because 1 D went in. What's the maximum number of electron domains I can have? 6. So this was 5 electron domains, so we've got 1 more. 5 electron domains. Now I would need to promote until I would need to promote, and then I would need to combine 6 orbitals. So I would have 6 orbitals go in. I have an s. I have 3 p's, and I would take 2 d's for the last 2. So sp3d squared. That is the last kind of hybrid orbital we have. So let's summarize them all in a table that you can use to keep track of these. Again, I'm not going to expect you to look at these pictures and go, oh, that's sp3d, although those are very pretty pictures. Let's summarize this all in a table for you. So I'm going to make this table. Number of electron domains versus hybrid orbital type. So the first kind we had was that carbon dioxide when we had 2 electron domains. So we combined an S and a P. The next one we had was the boron trifluoride. We combined 3. We had 3 electron domains. So the 3 we combined was an S and 2 P, so it was sp squared. In our ammonia example, we had 4 electron domains. What kind of hybrid orbital did we have? sp3. Are we starting to see a pattern yet? Yes. So if we had 5 electron domains, what would it be? You only have 3 orbitals. Good. sp3d. And then 6 would be sp3d squared. Good. That's it. By the way, this is all on page 391 in a handy little table that even has the pictures on it if you need it. And that will probably answer half of your questions about hybrid orbitals that simply ask what kind of hybrid orbitals you have. If you can determine how many electron domains, which is the first step in Vespers anyways, then you can determine what the hybrid orbital type is. How do you feel about that? Do I have that table? There it is. So again, if you have 2 electron domains, your sp, 3 your sp2, 4 your sp3, 5 your sp3d, 6 your sp3d squared. Questions? All right, so next time we'll cover the last couple of theories of bonding.